is, we could say, debate from what we have discussed so far. So we have chemical equilibrium, acids and bases, okay, then acid equilibria, including this solubility equilibria. So when we're talking about chapter 17, we're talking about here the concept of entropy, free energy, and equilibrium. So in such way, it's still directly related to what we have discussed so far. Like what we called, started with chapter 14, which I mentioned to you as the most important chapter. Okay, so the concept of this entropy, free energy, and equilibrium, we should learn about this by the end of this what we call chapter. Okay, so if you're going to recall, in your chapter 6, in Gen Chem 1, you were introduced to the concepts of thermodynamics. So thermodynamics, we could say, is just answering the question, will a reaction takes place? Okay. And one thing that you have learned in thermodynamics, if you're going to recall, is the concept of enthalpy. Are you still familiar with that? What's the symbol that you remember from enthalpy? It's delta what? Enthalpy is the delta H. And we say if it's a positive, what's the term synonymous to that?
Exergonic.
So it's endothermic. And if the delta H is negative, you have what we call an exothermic reaction. So if we're going to deal with this meaning of endothermic and exothermic, endothermic is where energy is absorbed by the given system, okay, during the reaction, while exothermic is energy is released or given up by the system. Now, they try to look at this concept of this what we call entropy, free energy, and equilibrium, because in chapter 6, we are introduced, I don't know if you still remember, the first law of thermodynamics. Anyone wants to say what's the first law of thermodynamics? The first law of thermodynamics is what? Conservation
of energy.
Yep. Energy cannot be created nor destroyed, can only be converted from one form to another. So that's what of these, one of the enthalpy is one of the thermodynamic entity. Now in chapter 17, we're going to increase this thermodynamic entity. Okay. Now, the first thing that we're going to ask ourselves is, what is this concept of spontaneous? So when we're talking about a spontaneous thing, okay, we're talking about a physical or a chemical process that occurs by itself. So when we're talking about spontaneous, it does not require any outside force. So if you put it on a certain environment, that process will happen on its own. Okay, so we could say the reaction happens spontaneously. The physical or chemical reaction or process or change happen spontaneously. So what are these spontaneous reactions? Just like this one. When you have a waterfall, it's always what? The water comes from a higher place going to lower place. Okay, and if we ever put a sugar in a cup of coffee, what will happen? The sugar will dissolve itself. If you stir it, it's just going to make the dissolving faster. But on its own, the sugar will dissolve itself. So the same thing with this one. If you have a temperature of 0 degrees Celsius, okay, if you put water below it, below the 0 degrees Celsius, the water freezes. But if you put that water or that ice above the 0 degrees Celsius, it's going to melt. And spontaneously, what we have learned from chapter 6, heat flows from a hot object to a cold object. That's why we call it heat, right? Because what do you think will happen if that entity travels from a colder object to a hotter object? Maybe you can call it what? Coldness. Okay. And then when you have a gas, it always expands in an evacuated valve. And then if you have a metal like iron, if you expose it to oxygen and water, it is spontaneously formed into rust. So what other spontaneous thing that can happen that we can apply in this course? Can we say failing an exam is a spontaneous process? Huh?
No.
Let's see. I try to what we call make a poll, so I could get your opinion. If failing an exam is a spontaneous process, I cannot just. I'm trying to look at the poll. So maybe I will just say true or false, but I cannot edit right now, so I just put here instead of showing you this thing, instead of saying melting point is the same as freezing point, I would I think I would change that thing. Just wait, not that one. Maybe this one. Oops. I'm trying to one that says the true or false thing. But I think I'm with what we call with that one. So I stop sharing. I'm just going to redo it again. Relaunch poll. Okay, so let's see. The statement, failing an exam is a spontaneous process, true or false? So just use the true or false here. And I'm going to explain to you why it's a spontaneous or not a spontaneous process.
It doesn't show on the poll.
So failing an exam is a spontaneous process, true or false? Okay, so where are the others? So at least it's going to clarify to you what will happen to you spontaneously. Okay, because we want to what we call I just want to assess your understanding about the spontaneous process. So instead of using that melting point there question, I just need you to use the true or false. Failing an exam is a spontaneous process, true or false? Okay, so 7 out of 7 versus 6. Okay, so the others are just what we call lagging in, and then don't listen, and then the exam comes in, the result is what? They're failing. Why? Okay, why do you think failing an exam is a spontaneous process? I'm going to explain it to you. Why do you fail the exam? Anyone?
Because you didn't study.
Okay, you didn't study. So you didn't study, that means there's no outside intervention. If you study, is there an outside intervention? Is
No.
there an intervention when you study? Yes. Okay, remember, what's the definition of spontaneous or spontaneous process? It happens
on its own.
On its own. So if you study, does it happen on its own?
Yeah, because whatever you study, you remember for the test.
It doesn't happen on its own, because if it happens on its own, that means you don't do anything.
Okay.
So failing an exam is a spontaneous process, because if you don't do anything, what will happen?
You'll fail the exam.
You fail the exam. Okay. So if you're going to what we call study, you're going to answer the problem set, you're going to look at the reviewer, you're going to take the quiz. There's an outside intervention there. It doesn't happen on its own. You make it happen. Okay. So I think this is one way wherein a chemistry concept would be, we could say, applicable to most of you. Okay. Now everyone's asking for extra credit, when in fact there are what we call the big credit that you can get if you do your ALEX. Okay, that Alex is 25% of your grade. That's 1/4 of your grade. And then you're asking for an extra credit that's just what, 5 or 10%? So which do you think is more impactful? Okay, which will have more greater impact? Okay, the Alex or the one that you ask for extra credit? Okay, so that is what we call the spontaneous process. For it to happen, it happens on this one. No outside intervention. That's why failing an exam is a spontaneous process, because you didn't do what you need to do. So spontaneously it happened. Okay, I hope it clears to the 6 students who says it's not a spontaneous process. Now, if I'm going to show you the picture on what the spontaneous process is. So for instance, this one. So you have a gas cylinder here. One is empty, one is full. But once you open it, spontaneously, what will happen? It will go on that one, right? But can the reverse reaction happen spontaneously? Can this system go back to that spontaneously? Yes or no?
No.
No, you have to have outside force. Just like, I don't know if you could see it, I have a pen. So what will happen if I release it? Spontaneously, it will fall. Now, can I ask my hand to make the pen go back to my hand? Unless, of course, I'm a Jedi, I can use the force to force this one to go back. But if not, I have to raise my other hand to put the pen on the previous hand. So that's what it means when it is what we call spontaneous. Okay? So whenever a reaction is spontaneous in one direction, most likely its opposite direction is non-spontaneous. Okay? Now, what they try to do is to predict. Can we predict if a given reaction is spontaneous or not? So the first thing that they did is to use what you have learned in Gen Chem 1. Does a decrease in enthalpy mean a reaction proceeds spontaneously? So these are some of the examples of spontaneous reaction and their enthalpy. So the first one is combustion. Okay, so the burning of the hydrocarbons is usually a exothermic reaction, and it happens spontaneously. And then the mixing of acid and base, okay, to form water, it happens spontaneously, and it is an exothermic reaction. However, there are also some reaction wherein you melt your water into liquid. It needs energy. It happens spontaneously. So the enthalpy that you have there is endothermic. And then you have this ammonium nitrate. When you put it in water, it dissociates to form the ammonium ions and nitrate. And again, it is an endothermic reaction. So what does it mean? A spontaneous reaction can happen to both what? Exothermic and endothermic system. So enthalpy is not enough. The delta H is not enough to predict if the reaction will be spontaneous or not. Why? Because you can have an exothermic reaction that is spontaneous, and you can also have an endothermic reaction that is spontaneous. Okay, so what they did is they introduced another thermodynamic quantity, and they call it entropy, denoted by S. Now, S is a measure of what we call randomness or disorder of a given system. Now, what they observe is when there is more order in a given system, S decreases. And if there is more disorder in a given system, S increases. So if you're going to look at the delta S that you have there, you just look at the order or the disorder or randomness after and before. You look at the difference, okay, after and before the system. And if the change from initial to final results in an increase in randomness. So you could say the delta S will be what? The final S is much larger than the what we call delta initial S, and the delta S would be positive. So there's an increase in randomness. Now, if it's the other way around, when there's what we call more disordered in the initial compared to the final, when the delta S will be less than 0. And what they have observed from the solid to the liquid and the what we call gas state, there is an increase in disorderliness. Okay, so whenever you have water or ice, that melts to give you what we call liquid, you could say the delta S increases. What does it mean? How are you going to interpret here? Water is more disordered than ice. Do you get it? What I mean? If you're going to look at the structure of water, since the water molecules are further from one another, they are more disordered compared to, let's say, the water molecules in the ice. They are arranged in a regular manner. So there's a high degree of orderliness if you are in the solid phase. So what they observe, they can use entropy to aid them to predict if a given reaction is spontaneous or not. So the way that they look at this entropy, so there's what we call the number of these microstates. So if you're going to look at the number of this microstate, so there's a constant times ln of W. So here you could see that the delta S that you have, the degree of disorderliness or randomness is higher in the final state compared to the initial state. So the way that you're going to look at this in terms of the W that you have here, so the final number of microstate is higher than the final, than the initial degree of what we call Wi. But I think it's much in terms of molecular or an atomic model. The slide is not going to be helpful, but this one is the one that's going to be helpful to you, showing you why solid is more ordered than liquid, or why liquid is more disordered than solid, and why vapor, or the gas form is more disordered than the liquid. And then if you also have this what we call solution. So if you're going to look at this, solution is more disordered compared to, let's say, the solvent and the solute. The solvent in itself and the solute in itself. And if you're going to look at the given system, this is the system at what we call initial temperature versus the system at final temperature. And if you're going to look at it, the disorderliness increases with temperature. So the higher the temperature, the higher is the disorderliness. Now, ask yourself, around the world, which happens spontaneously? A system that creates order, or a system that creates disorderliness? When you are a child, what do you usually do?
You make a mess of everything.
Again, what?
You make a mess of everything.
Okay, you make a mess of everything. If ever when you are a child, you have a lot of toys, you ask, your parents ask you, okay, don't make a mess. It's easy to make a mess, right? It takes effort to make it in order. Because whatever happened around the universe, usually the degree of disorderliness is the one that will happen spontaneously, right? That's why in 2016, the one who promised, I am the order, I will bring order, won the election. Because he promised he will do everything. I alone can do it. And, American people believing him, voted for him. Unfortunately, COVID hit him. Okay. And one of the things that COVID had is what we call the brain damage, because he believes that he won the election even though he is behind by 7 million votes. So I think that's the effect of COVID. Okay, but the way I'm trying to show you here is in the universe, what happened, okay, in a given system is chaos is the preferred thing to happen. Whenever a spontaneous reaction happened, most likely the final condition is more disordered compared to the initial condition. Okay. And if we're going to look at some of these chemical systems, so for instance here, so this is what? The evaporation of bromine. So if you're going to look at it, which is more disordered, or how could we predict the delta S for this? Okay, so this is the evaporation of bromine, and this is the sublimation of bromine. So in both cases, the delta S is equals or what we call more than to 0. So what does it mean? More ordered or more disordered in both systems? There is more disordered, or we could say the term that we could use is it becomes less ordered. So I want you to what we call not confuse when we discuss a given system. Okay, so let's try to look at what is this entropy, because entropy we said now refers to the randomness. So delta H is the enthalpy, and enthalpy has something to do with the heat of reaction. Now delta S now refers to randomness. Now this is what we call a thermodynamic quantity, and just like enthalpy, it is a state function. So when you say a state function, okay, it depends on the final and initial condition. So when you're talking about the state function, these are properties that are determined by the state of the system, regardless of how that condition was achieved. So it's just like when we go to York during exam, okay? So your initial destination is your home, and your final destination is York College. It doesn't consider whether you went to York by walking, you went to York by swimming, by skydiving, by taking the train, okay? But what it do is just, it's looking at where you came from and where you're going. It doesn't look at how you achieve your destination, okay? So for instance here, if you're going to look at this, so this is your final destination, and this is your initial what we call the place of origin. So the one that it's looking is just the difference between this and this in terms of the elevation. It doesn't look at whether you took this pathway or you took that what we call pathway. Okay, but the potential energy that you have here is just the same, because what you're looking here is just this one here and this one, the difference. It doesn't look whether you do it like this or you do it like that. It just look at the difference of this thing, like the potential energy. So that's what we call a state function. And state functions are many, like potential energy here, enthalpy, pressure, volume, temperature, and the entropy that we're looking for. So if we're going to look at this entropy, okay, they have different, we could say, value depending on the condition. So look at the water. Water at liquid state is 69.9. Water in the gas phase is 188.7. Does that make sense? That the gas phase has a higher entropy compared to the liquid phase? Does that make sense?
Yes, the gas molecules are moving more randomly.
Okay. Yes, because gas is more disordered than liquid. So the same thing with the bromine. The same thing with the iodine. And then maybe by the end of the day, we can answer the questions, are diamonds forever? In a practical sense, because you have carbon in the diamond form and carbon in the graphite form. So if you're going to remember your Gen Chem 1, it says here, based on this interpretation, what does it mean? Which is more ordered between the two? Which is more ordered between the two? Based on the given value. So the more ordered is the diamond because it has a lower entropy value. And as you could see in your Gen Chem 1, what shape is the diamond? The carbon are arranged in, you still remember that molecular shapes? What do you call that shape? Okay. They are arranged in a tetrahedral form, while the graphite, they are arranged in some sort of a layer, right? So there's a layer of the carbon there, and then there's a layer around here. So that's a little bit more disordered compared to the diamond. Okay. So that's what it means here. So let's try to predict whether the entropy change is greater or less than 0 for each of the following process. The freezing of the ethanol. Okay. What can you say about the delta S for here with respect to 0?
It's going to be less than 0.
The freezing of the ethanol. So if you're going to look at here, initial is liquid, and then the final is solid. So your delta S will be a negative. It's less than 0. Now, evaporating a beaker of liquid bromine at room temperature, what would be the delta S of that? Anyone?
Greater than 0.
Okay. So there's an increase in orderliness, or an increase in disorderliness, or a decrease in orderliness. So dissolving glucose in water. How would be the delta S? Will it be positive or negative?
Is that also greater than 0?
Okay. So this is going to be greater than 0. So the delta S would be positive, because that could be the next question, other question that you can ask. What's the delta S? And here, what could be the delta S? A positive or a negative value?
A negative value?
So this is a negative value. That's less than what we call 0. Okay. Now, in Gen Chem 1, you learn about this first law of thermodynamics. Energy can be converted from one form to another, but energy cannot be created nor destroyed. Now, in Gen Chem 2, you will learn more about this, what we call law of thermodynamics. So in the second law, the entropy of the universe increases in a spontaneous process and remain unchanged in an equilibrium process. So as I told you, if you're going to look at the events that happen in the universe, okay, there are more times that the world is at war compared to the times that it's at peace, right? That's why if you're watching beauty pageant, you can ask, you can see there, what do you want the world to be? Oh, peace and prosperity, because it's so hard to have a more ordered system. Okay, so the second law of thermodynamics explains this. So what does it mean? In a spontaneous process, okay, the delta S of the universe is increasing. It's what we call greater than 0. Now, in an equilibrium process, we could say that the delta S is equals to 0. The entropy of the system is equals to the entropy of the surrounding. Now, what's the thing that you need to remember here in terms of the calculation? So since this is similar to your enthalpy, so you can also replace the enthalpy here with just entropy. So the standard entropy of a reaction is the entropy change for a reaction carried out at 1 atmosphere and 25 degrees Celsius, the one with a degree sign. So if you're going to look at this, so this is the what we call typical equation. So if you want to get the delta S, this is just the sum of the product of whatever the coefficients that you have here times the given S, okay, minus the sum of the product of the coefficient times the delta S. So that means the delta S value should be given to you. So this is the simplified form that you have. Okay, so let's try to what we call solve this problem. So what I'm going to do is I'm going to put the value that you have that we have in this given system and for you to calculate them.
Professor, could you back up to the last slide for like a second? Let me just. I think.
So I'm going to put the value here. So you start doing the calculation. So this is 39.8. Just trying to what we call. So here this is 193 and this is H2 131. HCl is 187. Oops, sorry. And this one would be 131 and 223. Okay, so let's try. So the first one, you might ask yourself, can we predict delta S even without the number given? Do you think we can predict what would be the sign of the delta S even without the number? The answer there is of course yes. Okay, so if you're going to what we call do this thing, so what is the delta S there? Predicting it. So the way that you're going to predict is look at the physical state. So this is what S, and then G. So as you could see here, you have one S here and one S here, but you have an additional G. So your prediction will be here what? Positive or negative? Will you get a positive sign or a negative sign? So based from this, it's a positive. That means your system will become more disordered. And to prove if your prediction is right, so you're going to gather this. So these are all what? 1 mole. So you can just put it as 213.6 plus 39.8 minus 92.9. And I think somebody already predicted it to be equals to 160.5. Which is a positive sign. Okay. Now, how about the second one? Can you predict if the delta S value is positive or negative? The answer is yes. Okay. And if you're going to look at this, there's what? Gas, so that's 4. And then you have 2 here. So that means the delta S that you get here is negative. From 4 substances, you're just going to have 2. And to test if it's right, so the way that you're going to do it, so this is what? 2 times 193 minus 192 plus 3 times 131. And what do you get?
Negative 199.
So you're going to get there a value of around negative 199. Yeah, you just hope that the 20 points problem solving are like this, right? Now the last one here. So as you could see there, it's almost close, right? You have two gases at the one side and two gases also at the same side. So the value that you will get here would be a small value, and it can either be positive or negative. Okay. So if we're going to check what it is, so we could say 2 times 187 minus 131 plus 223. So you can get here either a positive or a negative, but the value will not be high, maybe less than 100. Okay. So what do you get here?
I got a 20.
Okay, so it's a 20. So it can be positive or negative based on what you have here. Now, what do you need to remember about the entropy changes? When gases are produced or consumed, you have to look at if the reaction produces more gas molecules than it consumes, then you have a positive delta S. If the total number of gas molecules diminishes or decreases, then your delta S will be negative. Okay. And if there is no net change in the total number of gas molecules, then the delta S can be positive or negative, but the value will be a small number. Okay. So let's go here. We don't going to do any what we call calculation, but we're going to predict what's the delta S will be. Will it be positive or negative? The first one.
Going to be negative.
Okay. So if you're going to look at here, gas, and then you have liquid, so negative. Everyone agree with that?
Yes.
Okay. Now how about this one? A solid forming to what we call gas. Is it a positive or a negative?
Positive.
So that's a positive. Okay. And this one. So it's similar to the last problem that we have. We
Either
cannot
or.
predict whether
Could
it
be
is a
either
positive
positive or negative.
or negative, but it will be a small delta S value. That's the one that it was what we call tells us about it. Okay. So if we're going to look at the entropy changes in the surrounding that we have, as I have told you, based on the what we call entropy changes by looking at the surrounding here. So if you have an exothermic process, your delta S of the surrounding is usually a positive value. There's an increase in the entropy. But if you have an endothermic process, the entropy of the surrounding is less than 0, or what we call negative. Now, synonymous to this one is also the so-called third law of thermodynamics. So there's more law of thermodynamics that is covered in this chapter than chapter 6. So we have the first law, conservation of energy. Second law, as what we call entropy increases in the the entropy of the universe increases in a spontaneous reaction. That's the second law. Now, in the third law of thermodynamics, it states here, the entropy of a perfect crystalline substance is 0 at the absolute 0 of the temperature. So what does it mean? When temperature increases, there's also an increase in the entropy value. Okay. Now, the one where the entropy value will be fixed is when they are in what? The melting and the boiling point. So that's where you have the delta S of the fusion and the delta S of the vaporization. But if you're going to look at this as the temperature increases, the entropy increase. And we can apply here the microstates. Okay. And the way that we look at this is the table that I showed you, wherein the delta or the delta S of water in liquid is much higher than the delta S of the water in the gas form. So this is how it looks like. Okay. So the question that we have now, can we predict now whether a reaction will be spontaneous using both the delta H and the delta S? Remember the dilemma that we have at the beginning. Delta H, you can have a positive and a negative value, and the reaction is what we call spontaneous. But the delta S, usually what? In most spontaneous reaction, the delta S is positive. Or in most spontaneous reaction, there is an increase in entropy. Now the question now, using these two thermodynamic quantity, can we predict now if a given reaction will be spontaneous or not? Okay. And before we answer that question, they introduce another thermodynamic unit. And this is now what we call the free energy. Now, the free energy as we go on is related to the delta H and the delta S. Okay. So if you're going to look at the free energy, they use the symbol G, and you might ask why, just like the entropy, why is it S? Okay. Now for G, the answer there is because the one who studied it was Gibbs, Willard Gibbs. And the standard free energy of the reaction is defined as just the free energy change for a reaction when it occurs under standard state condition. So what does it mean? It's the same thing with the enthalpy and the entropy. Okay, they look at the difference between the sum of the free energy of the products minus, okay, the sum of all free energy of the reactants, like this one. So this is just one of the equation that you will know. And I call it the Big Mama equation. There are a lot of delta G equations that you will encounter. And this is one of the common one. And this is just synonymous to what? Getting your delta S and delta H. And whenever you have a degree sign, that means you need to have the so-called standard condition. So what is that standard condition? 1 mole of compound. Okay. What's the temperature in the standard condition? Anyone? 1 atmosphere and
25 C.
one atmosphere and 25 degrees Celsius. So that's what we call the standard condition. And there's also a value of this, what we call delta G. If you have the chemistry book, usually they have an appendix that listed the delta G, the delta H, and the delta S. Okay. And you will see the difference between the delta G, the delta H, and the delta S. The delta G and the delta H, they can have a value equals to 0. However, the delta S, you cannot have a value that is not equals to 0 unless, when is your delta S equals to 0? Anyone?
Equilibrium.
Is it in equilibrium? No, when we're talking about the delta S of a given what we call species, when is the delta S of the species equals to 0 compared to the delta G and the delta H of a given element or a given element or compound. Okay, you only have a delta S value on a given species or substance when the temperature is equals to absolute zero. Okay, now the delta G and the delta H, there are conditions where the value that they have is equals to zero. That is when they are in their standard state. Okay, you will learn about that. So here, the delta G of any element in its stable form is equals to zero. The same thing with the delta H. Okay, so that's the thing that you're going to remember. Now, as I told you, this is just one of the equations that you need to get the delta G. So this is when the delta G is given. Okay. Now, what if it's not the one that is given? Are there anything that you can do? Yes, you should still have any other ways to do it. So maybe we could say, what are those other delta G? You will encounter it, okay, in this chapter. So as we know, in a spontaneous reaction, the entropy of the universe is increasing. That means the delta S is positive. And in an equilibrium process, the delta S of the universe is equals to zero because the delta S of the system is equals to the delta S of your surrounding. Okay. Now, how are we going to put into action the knowledge that we have with respect to the delta H and the delta S? So what did we say earlier? Delta H, positive or negative, it can give be spontaneous, but delta S, for it to be spontaneous, is always what we call a positive. Now there is a relationship on that leads us to delta G, and this is this one. So if we have initially the big mama equation, I call this the granddaddy equation. And that is the Gibbs free energy. And now, with the delta G, we can now predict if a given reaction is spontaneous or not. Okay? How? So they found out that if your delta G is less than zero, or when it is what we call negative, it is spontaneous in the forward reaction. If the delta G is more than zero or positive, the reaction is non-spontaneous, but the reaction will be spontaneous in the reverse direction. And if the delta G is equals to zero, then the reaction is at equilibrium. Think about it. Okay. So we now have a thermodynamic quantity to predict whether a given reaction is spontaneous or not. And it's a combination of both the enthalpy and the entropy. Okay? Now, as I have told you, you have to remember the so-called standard states. For gas, is it the one with 1 atmospheric pressure? In liquid, you should have a pure liquid. The solid, it must be a pure solid. Now, if it's an element, the delta G is always equals to 0. Now, for the solution, you always have to make sure that it is equals to 1 molar. Okay? So let's try to look at the standard free energy changes for the following reaction. And then again, I'm going to give to you the value and try to calculate it on your own. So you might say, oh, you wish this is how the exam will be. So you have here 394. So that's a negative. Negative 237.2. This one is negative 50.8. And what do you think the value of this? Oxygen. That's 0. And if you have the magnesium here, so this is equals to 0 also. And this is equals to negative 569.6. So try to solve it. Going to get some water, but I like you to solve it. So what did you get? Oops. So the first one, you got negative 818. And the second one, you got 1139. So how do we interpret this? So the first one is what? Spontaneous or non-spontaneous?
First one is spontaneous.
Okay, so since you have a negative value there, that's a spontaneous reaction. So what does it mean? This reaction will happen on its own. Now the second one, what happened here? It's a non-spontaneous reaction. So what does it mean? Whatever you do, you cannot make magnesium oxide to form magnesium or oxygen unless there's an outside intervention. So what happens spontaneously is when you have magnesium that was oxidized with oxygen. Are you familiar with sparkler? How do you make the sparkler react? You need to have light, flame, right? And what happens is there's a sparkler. You're going to produce these flashy lights. So that's the reaction of magnesium with oxygen. And at the end, you're going to have the residue magnesium oxide. So that's what it means here. Okay. Now, how do we look at this in terms of action? How do we utilize this so-called Gibbs free energy? So it has something to do with, I don't know if you're familiar with this one, a refrigerator. Now, the question that I would ask you, do you think refrigerator is a good engine? Because if you're going to look at the refrigerator, this is what? If you're going to look at the efficiency, this is the formula that you need. So the way that it works, there's a heat reservoir, okay? And then there's a heat agent. So any heat that goes to the what we call sinks, that's the temperature at the cold temperature. And the work is the one that they have. And unfortunately, refrigerator is not a very efficient engine. Okay. You know what the refrigerator do? It's an engine that produces coldness. Okay. So this is one of the applications of this, what we call concept, the free energy. But the one that I would ask you to look into detail is this one. So here, it can predict to you what will be the delta H giving, the delta G given the delta H and the delta S. Okay. So if you're going to look at here, if this is a positive sign and this is a positive sign, what will happen? Everything depends on the T value. Because positive, positive, so that means for this to become negative, this value here should be more than the delta H. That's why it says here, reaction proceeds spontaneously at high temperature. At low temperature, the reaction is spontaneous in the reverse reaction. So that is when you have a positive and a positive on both of them. So the higher the T will give you a delta G, a negative delta G. The lower the T will give you a positive delta G. Now, what is the one that will give the delta G always a positive? When you have a positive of this and a negative of this. Because negative times negative will give you what? Negative times negative will give you a positive. So everything will be a positive. So that means the reaction is non-spontaneous in the forward direction, but is spontaneous in the backward direction. Now, the one that will always give you a negative is when delta H is negative and delta S is positive. Because a negative times a positive will give you always a negative. So negative and a negative, that will give you a negative. So these are the multiple choice questions that you have in the fourth exam. And then what happened when you have a negative here and a negative here? So again, it depends on the value of T. So for the delta G to be negative, your T should be small. Okay, so the delta G is negative when you have low temperature. If you have a low temperature here, okay, that will give you a negative value. But once this one increases, then that will give you a positive delta G. Okay, so those are the things that you need to remember here. Now, the next thing that I will talk to you is, okay, Professor, you said the delta H. Now, what is the effect now of the on the delta, we could say delta S, delta H, and delta G when you have a system at equilibrium? Just like this one. The temperature and the spontaneity of the reaction. So the way that you look at this, so let's say we have a system like this. Calcium carbonate solid producing calcium oxide and CO2. This was discussed in your equilibrium. So it was given there that these are the value. Okay. So you're going to ask yourself, at what temperature will this be spontaneous? So using that value, what do you get in terms of delta G? if you're going to use that value, okay, at 25 degrees Celsius, delta G is 130 kilojoules per mole. So what does this mean? Is this spontaneous or non-spontaneous?
It's non-spontaneous.
So this is non-spontaneous. Now the question now is, at what temperature will this system become spontaneous? So what do you need to do? What would be the value of your delta G for the system to be spontaneous?
Yeah, you should set delta G to 0 and then solve for T.
Okay, so the way that you're going to do it, your delta G should be 0, and you need to find what will be the temperature. So if you're going to look at the relationship there, so once you have a 0, so you have a delta H minus T delta S. So what will happen? You can have T delta S equals to delta H, right? And to get for the temperature, you divide both sides by the delta S. So in doing that, I could just put here 177.8 kilojoules per mole divided by, look at the unit, 0.1605 kilojoules, or it's not kilojoules, it's JK, kilojoules per K mole. So if you're going to look at the units there, what's the one that is left? Kelvin. So how much is this equal to? Anyone? This is equal
1,000,
to
1,000,
1,007
107.8.
or 8. Now, if you want to convert it to Celsius, it becomes, how do we get with 835? So 1108 minus 273. So that will give you 835 degrees Celsius. Questions so far? Before we go on another example. So we can also predict phase transition using the so-called Gibbs free energy. So remember, whenever you have a system at equilibrium, what's the value of delta G? Just like this one, okay? We have a system at equilibrium here. Whenever we have a system at equilibrium, delta G is always what we call 0. So let's look at this system that we have been discussing since chapter 11, the evaporation and the condensation system. So this is the system that it has. Now, if you want to determine the delta S, how are you going to do that? What would be the value, do you think, of your delta S? A positive or a negative? So this is what from here? What is the delta S of this system?
Positive.
Will it become ordered or more disordered?
More disordered.
So this will be
Positive.
positive. So you have to predict it the way you understand. Okay, so this becomes more disordered. So this is a delta S of what we call positive. Now, what if we want to get the value? So we still do the value that like this. We rearrange it in such a way the delta S is the one that we get here. Okay, so if we're going to do it, how did we end up with this one? So you have again delta H equals to T delta S. And then we just divide them by the temperature. What do you think is the temperature that we have here? What do you call the temperature? Let's say if you have water, what would be the value of your T there? What is the temperature associated with this? Anyone?
100 degrees Celsius.
100 degrees Celsius. And what do you think the delta H here? That's the delta H of the vaporization, which is 40.79 kilojoules per mole. Divided it by 200, oh no, not 200, 373 Kelvin. I think it's there. Okay. And the value that you will get is this one. 109. So what does it mean? The change in the entropy from the liquid water to the gaseous water is 109 joules per k mole. Does that make sense? Does that value make sense? Hello.
It's a positive S, I would think so.
Yep. Did that make sense? It makes sense because the gas water is more disordered than the liquid water. Okay. Now, I leave this up to you because this is not the type of questions that we have. So I just want to be direct here. But in one of our sessions, I'm going to go back with this one. So this is just the transition that you have from solid to liquid and liquid to vapor for benzene. Okay. But what do you think the delta S value here for both of them? What do you think the delta S value that you will get?
Solid to liquid is positive, and liquid to gas vapor is positive.
So both of them are what we call negative. So the way that you're going to do there is just similar to what you have. I think we can discuss it. All we need to do is what? What do I put here? The 109, 10.9 kilojoules divided by what? 273 plus 5.5. And here, I would have 31.0 kilojoules per mole divided by 273 plus 80.1. Why do I need to add 273?
Convert to Kelvin.
Because we're converting it to Kelvin. Okay. Everyone clear on that?
Yes.
And all we need to do there now is get the value. So what do you get? So if you're going to kilojoules per mole, and this is K. Kilojoules per mole and K. And you will have here as kilojoules per K mole. So I will have here what?
Did you get 0.039?
0.039. Yep, that's the right one. And this one would have 0.0. This is what I get. Get 8.849. Maybe on my eyes is No, I get so 0.0878. Am I missing something? Oh, it should be 80 point. I think this is at a 30. It should be, oh yeah, it's a 31.0. Yep.
I got 0.8, 0.08779. So it's
Yeah.
gonna
So if you're going to round it up, it will be
be
8
0.
because I need to express it in 3 significant figures.
Yes, that's right.
Okay. Now, let's relate this chapter with chapter 14. How is the Gibbs free energy related to chemical equilibrium? So what does it mean? You're going to have another equation for G. So you started with this, delta G is equals to standard delta G plus RT, L, and Q. So what's the difference of this G with a degree sign compared with just G? Anyone? What's the difference between the two? One is at standard state while the other one is at any other state. So when we're talking about standard state, 1 atmosphere, 25 degrees Celsius, 1 molar. Now this one is at any other condition that is not at standard state. Now R here is the gas constant. T here is the absolute temperature. And you have here the Q. What's the Q? The quotient. The one that you have learned from chemical equilibrium. Now, the idea here is you want to relate delta G with K. So you're going to use this equation to derive that relationship, because at equilibrium, what will happen? Your delta G is equals to 0 and your Q becomes K. Okay, and when that happens, you end up with this equation. So what does this equation looks like now? So you just transpose this to another what we call side. So you end up with the delta G minus RT, L, and K. That is what we call the rat-link equation. Here, again, this is another equation that you need to know. Now, if you're going to ask yourself, how is this related, this free energy that we have? What's the use of this one? So from the word itself, free energy. So usually it looks at the energy that can be used. Maybe you can use that energy to work, or you're going to need that energy to do a work. Okay. So when delta G is less than 0, that's what? Spontaneous or non-spontaneous? When delta G is less than 0, will it be spontaneous or non-spontaneous?
Spontaneous.
Okay, so that would be spontaneous. So as you're going to look at here, so this is the free energy of the reactants and this is the free energy of the products. So from this, will you produce energy or you need energy?
You'll produce energy.
So you produce energy. So that means you can have the energy available for work. Now, on the other hand, if the delta G is more than 0, what does it mean? You need energy. So this is where the concept of spontaneity happens. Remember, how do we describe spontaneous process? It happens on its own. So here, this illustration show you that, hey, it produces energy, the free energy. So it can happen on its own. But this one, it needs energy. It needs outside intervention. for the reaction to proceed. Okay, that's why, what's the statement that we have? A spontaneous reaction in one direction will be what in the opposite direction? So if the
Non-spontaneous.
forward reaction is spontaneous, the backward reaction is
Non-spontaneous.
non-spontaneous. Okay. Now, how is this rat link that we have, the delta G equals to negative RTL, and okay, what does it gives us? What's the information that it will give us? So we will have the reaction like this one. K, if the K is more than 1, so your L and K is positive, then the delta G is negative. When does K more than 1? Remember the reactants producing products. So K is more than 1 when there's more products compared to the reactants. So that means the forward reaction happened. And in terms of delta G, the forward reaction will happen if the reaction is spontaneous. Now, if the forward reaction has a negative delta G, so that means it will not happen spontaneously. Then the one that is favored is the backward reaction. So what does it affect on the K? You have more reactants than the product, giving you a value that's less than 1 and a negative ln K. Now, if you have a system at equilibrium, your delta G is 0, your K is equals to 1, ln of 1 is equals to 0. So let's try to look at an example here. So using the data listed in Appendix 3, which I'm going to provide to you, calculate the equilibrium constant for the following reaction. So this is in terms of delta G. So this is 0, this is 0, and water would have negative 237.2. So what's delta G here? So we could just say 0 minus negative 272, wait. 0 minus 2 times negative 237.2. Right? And that would be equals to what?
$474.4.
400.
74.4.
474.4. But that's just the delta G. What is being asked? Kp. So we're going to use the rat link. Delta G equals to negative RT ln Kp. So what are the other informations that we have here? We can divide this by both what? Negative RT. So I have a 474.4 kilojoules per mole. I can multiply it with 1,000 joules per kilojoules. And then negative 8.314 joules. You following me? K mole times, what's the temperature that you have here? 25, so that would be 298 Kelvin. What do you get?
Got negative 191.5.
So you get negative 191.5. Now, what would be the Kp? Or before we answer the question, can we predict if Kp will be positive or as a very big number or a very small number?
Very small.
Okay, so we can predict what Kp will be. Why? Because we have the delta G. And since we have a positive delta G, so that means this would be less than 1. So how do we get the Kp here? So Kp raised to the E raised to the negative 191.5, and that will give you
6.8 times 10 to the negative 84.
okay. So it's a very small number. So I'll stop here and I will give you quizzes, okay? For the thing. And